Okay, hello everyone, and welcome back to the second session in this series of lectures/workshops in data-driven linear algebra. So I'm going to start off by going through a question that came up right at the end of the stream last time, and also a point that I said I would mention and forgot to. But if there's any other questions from last time, we shouldn't be so rushed in this session, so feel free to pop them in the chat now, and we can address them at the start. I'm assuming I can be heard okay, the screen's coming through, it's all clear. If not, please do say in the chat. Okay, so the question that came in right at the end of last session was about where you can go to learn more about singular value decomposition to get a more comprehensive view than this introduction. And so if you want to have a mathematical view of the singular value decomposition, there are a lot of great and free resources on the internet if you just search for singular value decomposition tutorial. In fact, there's many different universities, MIT, Stanford, for example, that have very good course notes on the singular value decomposition. But if you want to have some resources that are in a similar style to this series, in which we tackle the singular value decomposition in a very data-driven way, kind of focusing on things rather than as a mathematical matrix, as like a linear map, focusing on things as like a data set and actually doing the singular value decomposition on that data, well then a really good book is this one that I put here. And that is Data-Driven Science and Engineering. It's a book by Steve Brunton and his co-author, I forget what his surname is, his first name. But this is a really good book. It focuses on a lot more than the singular value decomposition. It's basically, machine learning and all forms of data reduction. It's a really fantastic book, and a lot of the ideas in this series are inspired by this book. It's quite pricey, but you can probably find places where you can get it for free. Or if you go to the website for this book, if you just search for the name, there is an associated lecture series from a few years ago in which Steve Brunton actually presents these ideas. So feel free to check those out. But the book is an invaluable resource. And so the second point I wanted to mention before we get started is we talked last time about how we had to kind of quite awkwardly have our data matrix represented with the columns going vertically. So the observations were these vertical columns rather than, as we would like, having them horizontally. And so the reason we did this was to be compatible with the common definitions of the singular value decomposition. But it would be nicer to have our data represented something like this, but that would have led to maybe some confusions. But I said, I encourage people to go and have a try at doing the singular value decomposition with this form. I was going to give a hint as to how you would do that. And it all comes down to, if we have our normal data matrix X, which looks something like this. This is the one that we're familiar with from last session. And this is one in which we have these observations as columns. Well then, if we transpose that, we'll end up with something like this, this highlighted thing here. And this is kind of how we would like to represent things. We'd like to know what the singular value decomposition is of that. And so, this is just the matrix X transpose. And we know what X is. We know that X is U sigma V transpose, where that's the singular value decomposition of X that we're familiar with. And so what we can do is simply take the transpose of that singular value decomposition. And what we would get if we do that is this series of matrices on the right. And it's important to know the rule that if you transpose a product of matrices, it's the same as the product of the transposes, but in the opposite order. And so what we're going to end up with is V transpose transpose, which is just V itself again. Sigma transpose, which is just another diagonal matrix. Actually, we probably should call that sigma transpose. And then we're going to end up with a U transpose at the end. And so we could simply define these to be matrices U prime, sigma prime, and V prime. And that's our new singular value decomposition. But the important thing is that because we swapped the U's and V's around, so now we define U prime to be V and V prime transpose to be U transpose, we flip the meanings of these matrices U and V. And so if you want to interpret the SVD, you have to bear in mind that those are now flipped around and that will also have consequences when it comes to representing the SVD as a sum of rank 1 matrices. So it's not perfect, but you can do that sort of thing conceptually if that helps you think about the SVD. So let's have a look at what we're going to be talking about today. So we're on session 2 now, and we're going to start with quite a big recap. So I appreciate that last time there was a lot to cover, and it flew by pretty quickly. So we're going to start with a recap of all we saw and hopefully try and distill down some of the key ideas so it's kind of a bit clearer what happened and the importance of what happened in last session. And so we're going to do a recap of that, and we're also going to introduce this thing called the economy SVD. I was going to leave that till a bit later, but we're going to add that to the start now. We're then going to have a quick recap of what an eigenvector and eigenvalues are, and then we're going to use those to actually compute the SVD. And we're going to have an example of actually computing that. Then we're going to follow up by comparing some different methods of computing the SVD. The one we're going to look at is nice in theory, but is very inefficient in practice. And then we're going to finally talk about how we choose the best point to truncate our rank 1 representation. But I'll mention that a bit more later. And then once we know how to compute the SVD and we have a good conceptual understanding of what's going on, not theoretically, but in a data-centric way, well, then we can move on next session to looking at some applications of that for a wide variety of problems. So let's start with a recap of what we looked at last time. So one of the key ideas I wanted to get across at the start was another way of thinking about matrix multiplication. So we're familiar with the standard way of multiplying matrices, in which if we want to have a matrix product AB and we want to know what is in the ijth position, then what we do, we kind of sum along this kind of this temporary or extra variable k, which is going to go along the rows of A and down a certain column, or the jth column of B. We times all those together and we add them up. So we have a matrix or two matrices like this, and we want to know what's going to be, that's going to give us a matrix that looks something like that. And we want to know what's in this position. Well, then we're going to take that row of A and that column of B, and then we're just going to times these against each other like that. And then we add them all up. And that's the standard definition of matrix multiplication. But that's not a very intuitive way of thinking about matrix multiplication, especially when we're in a data-centric context, because when we're dealing, with data, we think of our matrices as either kind of columns of predictors or rows of observations. And so there are nicer ways of thinking about matrix multiplication when our data has that sort of underlying structure. So there were two ways of looking at matrix multiplication, one as an inner product and one as an outer product. So the first one was the inner product, also known as the dot product. And so if we have our matrices represented like this, where the one on the left is row vectors and the one on the right is column vectors, well, then we can represent the product of those two matrices as a matrix of inner products or dot products. And a reminder, the dot product of two vectors is you take all their elements and just times them together. And you should be able to see that this is exactly the same thing as we were doing above, but now there's kind of an intuition behind it as to why that is true. And so we do those multiplications, we get a matrix like this. And it's actually worth noting that if we throw a diagonal matrix D into the middle of these, where this has entries D1 up to Dn, there's actually still a quite nice expression for what this whole product is going to be. And the answer is that rather than taking a simple dot product, we just take what's called a weighted dot product, where every multiplication in that sum is weighted by the entries D1 up to Dn. We could denote that something like this here. And so it also generalizes quite nicely to that case. And so the other thing we looked at was how we could do multiplication when the first matrix was columns and the second matrix was rows. And in that case, we could represent the matrix product as a sum of outer products. And outer products are the opposite of inner products, in which, so if A's matrix like this, and B's matrix like this, we times together all their elements to give us a square matrix. And then we can add those all together, and that gives us what the product of those matrices are. A bit harder to prove, but you should be able to work it out from that definition above. And so this is a really beautiful idea because these matrices here have a rank of 1. And so, they have a rank of 1. And so what that means is that we can represent this matrix product on the left as a sum of rank 1 matrices. And these rank 1 matrices, think of these as like your Lego bricks. They're the smallest unit of kind of data storage. Very simple representations of kind of the patterns in our data. And we also saw that if we had a diagonal matrix in the middle, then it's the same sort of idea, but now we weight each of these outer products in the sum by the values of those diagonals. And so those are very useful ideas for kind of understanding the importance of the SVD. So let's go back to look at what the SVD is. So when we were computing the SVD, we worked from the assumption that our matrix had these columns of observations. So each of these is an observation. That wasn't ideal, it's not the most intuitive way, but it helped with the maths. And it helped being consistent with the existing literature on SVDs. And so last time we looked at the examples of faces and trying to compute the singular value decomposition of a data set of faces. But I want to look at a different example this time, just to kind of widen the scope of topics we're looking at. And that's going to be signal processing. So we're going to imagine that this matrix here actually represents a song. And so each of these columns is going to represent kind of a frequency amplitude graph, so amplitude meaning loudness, at various different times. So this is the start of our song, and we move through the matrix through time. So this is kind of like the last sample that our song has. And each of those, we're going to have a each of these vectors represents kind of the frequency, and the values of the vectors is how loud that frequency is. So you can imagine here where we have this waveform here. That is probably going to be like, I don't know, something small 0 at the start, then maybe 1, 2, 1, 2, kind of showing how high those different frequencies are. And so that's what our data looks like. And we want a way of representing this, or I guess compressing the data into the key frequency profiles that make up our music. Because if this was random noise, it would be very hard to decompose this into anything else. But there's probably certain patterns that keep appearing. The bass drum is going to have a certain frequency, and that's going to keep appearing periodically. And so we should be able to decompose this down into a much simpler representation than it currently has. And we're making the assumption here that the number of predictors, so the number of frequencies, is much bigger than the number of timestamps we have. And the math still works out if that's not true, if that's the other way around. But in most cases, when we're doing the SVD, that's going to be a useful assumption. And so what we learnt was that we could write this matrix here as U sigma V transpose, and that's a singular value decomposition. This U contains the left singular values, the V contains the right singular values, and singular vectors, and then sigma contains the singular values. And so the sizes of these matrices, U and V are square, P by P and N by N respectively, and sigma is this P by N with some zeros padding the bottom. And so we found that these had kind of intuitive interpretations. The columns of U kind of represent a basis or kind of a palette for reconstructing our original matrix. In this case, these will represent individual frequency profiles that can be combined together to make the original song. And so it might be the case that one of these, there's like a bass drum frequency. This might be, the snare frequency. You might have frequencies for certain parts of bass guitar or electric guitar or whatever. And just, a warning here, this is a massive oversimplification. It probably doesn't look like this, but conceptually you're free to think of it in that sort of way. So each of these is just some sort of component that makes up our whole thing. And then the idea is these components are then weighted using these sigmas. So they're kind of saying, how important is this? So the bass drum is probably quite an important feature of the song, but there might be certain things that kind of, maybe it's just a specific bit of echo that you had at a certain time. That's going to have a very small singular value. It doesn't it's more noise than anything. It doesn't actually contribute much to the main information in the matrix X. And then these V's, there's two ways of interpreting them. If we look at the row vectors, these should be row vectors with transposes, row vectors V. What these correspond to is how the amount of each of these U's changes in the signal over time. So you can think of these as the time series for a certain U. So V1, for example, tells us how much of this component U1 appears as we move through this time series. And if we look at the columns, kind of cutting across these vectors, those tell us what mixtures of these U's we have to do to reconstruct a specific timestamp in our original matrix. So for example, if we take the fourth column here, that's going to tell us what coefficients we have to use with all these U vectors to give back the fourth vector in our time series. So a really kind of beautiful way of understanding this matrix X. And a few properties of those: U and V are orthogonal, and these sigmas are decreasing. They can be the same value, but they're decreasing, and they're all non-negative. Let's not forget that. So a correction I have to make. Last time I said that these matrices were unique up to the sign of these U and V vectors. You could negate, say, U3, and if you also negated V3, then that was fine. That was wrong. What I should have said is that they're distinct if all of these sigma i's are distinct. And actually, we'll see this a bit later. If the sigma i's are not distinct, then there's a bit more flexibility. But that will make more sense when we come to prove the existence and actually compute the SVD. And so we saw from this that using this property above of this matrix multiplication as outer products, that we could represent this SVD as a sum of these outer products weighted by the singular values. So each of these are these kind of rank 1 matrices made by taking U1 and V1 transpose. I'm missing a lot of transposes today. And then we weight those by these singular values. And so each of these are rank 1 matrices. They're very simple matrices. Basically, they're just, a single kind of frequency spectrum and the mixtures that you have of that over time. And so then the idea was we would then truncate this at a certain point. So truncate it at R, say, rank R, to give us an approximation of the original matrix X. And we call that X tilde, so tilde being approximation of rank R. And we basically cut off the U's after a certain R. We cut off sigmas, and we cut off the V's after certain R's to give us these smaller matrices here. And so I didn't really mention last time, why do we want to do that? Kind of what's the point of that? So let's explain that a bit now. And it's all about finding a balance between the complexity of the data and the actual accuracy of the data. Because whenever this R goes below the original rank of this matrix X, we will lose data. So we're going to lose some information and we don't have a perfect representation of the data. But we have a simpler representation of the data. Because you can imagine this original X has a really high rank. It's a really complicated matrix. There's a lot of kind of things at play. Actually reconstructing that X is very complicated, lots of different patterns in there. But it may be the case that you can represent, 99% of the information in X using only 5 rank 1 matrices. Well, in that case, you've lost 1% of the information, sure, but you've taken it from this kind of a rank 1000 matrix to rank 5. You've simplified it by a factor of 200. So the idea of this is it's finding the key important components of the matrix and using that to represent it while retaining as much information as possible. And that's why we're trying to do this. That's the goal. And actually, I'm going to quickly show an example. We'll look at some more examples in the next session, but just to motivate this. This is an example we shared on our Facebook. So we have a picture of a cat here, which we can represent as a matrix. We compute the SVD of this matrix, and then we end up taking 6 different rank R approximations. So we first look at a rank 1 approximation, literally representing this as a single outer product. And we get something like this. It's, not noticeably a cat. Clearly there's something in the middle. And actually we can see that this is actually just one single line that's been weighted different amounts across the image. And then we keep increasing the rank, so rank 5, 10, 20, and we start to see more of a cat appearing. And finally we get to a rank 80 approximation, and by that point, I mean, that's pretty much spot on. You can barely tell the difference between that and the original. But in doing this, we've reduced the storage of this image by about 80%. So an absolute great saving there. This is good for kind of efficiency of saving. But if it was a modeling problem, well, we've reduced the complexity of the model, a kind of actual understanding of what's going on here by a factor of 5, which again is great. We can reduce the workload of our brain in conceptualizing the problem by a factor of 5. That's great for us. Okay, so moving back to talking about the SVD, a few things also to mention. When we're doing this outer product here, why does it only go up to n? Because we had this these u's going up to p. Why does it stop at n? And the reason is because of these zeros here. So actually, if we represented this properly, we would have so if we look at u times sigma first, so rather than doing the whole product, u times sigma is going to be using these using these column-wise here, things here. Do I have that the right way around? No, I think I've got these the wrong way around here. Okay, well, let's ignore that point. The important thing is that these u's, once we're past n, start getting multiplied by 0. And so, this is correct, but let's not go into it. It's a bit more complicated than I thought looking back at it. So the idea is we get loads of zeros after we get past n, and so we just ignore those. And we only have to consider the first n here. So also worth mentioning, are UR tilde and VR tilde transpose, these kind of low rank reductions, are they still orthogonal? And the answer is no. I mean, we mentioned first time you can't be orthogonal if you're not a square matrix. These are no longer square, p by r and r by n. So they're definitely not orthogonal, but they do turn out to be semi-orthogonal. But if we take UR tilde transpose times by UR tilde, we do get the identity matrix. This is still the identity because all of these inner products still give the same values. So that works fine. But if we do it in the other direction, which would have been the identity before, this is no longer the identity because we're missing all of the outer product terms after R. And so this is not an inner product, this is not an orthogonal matrix, but actually we only need this first property in the rest of the session. So that's fine. And the same thing goes for V. But the good news is, at least sigma r tilde is now square, because before it was what's going to be a p by n matrix, but at least now it's square because we truncated it to r by r. So that's good. And also, it's worth mentioning that we could truncate it so that r is n. So truncate it to a rank of n. So when we do the truncation, we could truncate it directly at n. And we would end up with so the truncations at rank n, like this. And we actually have a name for these. We call these u hat, sigma hat, and still v transpose. And this is known as the economy SVD. And so it's worth noting that the economy SVD is not an approximation. If we only go down to rank n and not any further, it's actually still an exact representation of x, just using a bit less data. And the reason for this is that all of those zeros at the end, we can forget about these. Then they're not important. And so what this looks like kind of intuitively is if we take our original SVD, so this u sigma v, and then we basically just ignore these final u's here. And then we ignore all these zeros. So this becomes a p by n matrix and an n by n matrix. And we keep v exactly as it was before. This still gives us the exact same x we had before, but now we've missed out on all of these extra u's that weren't needed because they times to be 0. So you can imagine a case where we had like 3 observations n, but they had 1 million predictors each, say 1 megapixel images. Well, this is a really good thing to do because now we've reduced this matrix by quite a bit. We lose the orthogonal property we had before. U is no longer orthogonal. It's semi-orthogonal, like with this. But at least now we have sigma being symmetric. It's a square matrix now, so that's nice. And V is the same as before. So we'll just have to bear in mind, we're going to use this economy SVD for most of the session, that we only have one of the orthogonal properties, or one direction of orthogonality for U. And so we were talking about this, this kind of low-rank approximation being a good thing to do. It turns out it's actually the best thing to do. That we looked at this thing called the Eckert-Young theorem, which said that this approximation, so cutting off at a certain point R using the SVD, is in fact the best approximation we can make of X using a rank R matrix. So it's X R tilde, which is these tilde matrices here, is the best approximation. And that's using the Frobenius norm, which we defined last time. Basically flatten the vectors and then compute the normal Euclidean distance. It turns out it's also optimal in the spectral norm, which is another useful measure of distance in matrix space. Have a look into that if you want to, or you might know it already from analysis 3. And so choosing that this R, we saw that we could use these plots here. So our logarithms of sigma look something like this. And we probably want to pick out what we would call an elbow. And that's a place where this curve starts to flatten down. So for every rank we add, we don't get much benefit. We'll stop at that point and we'll truncate there. Another way of looking at it would be to take the sums of our sigmas and ask at what point do we have, say, 90%, 99%, or maybe even more of the information in X represented, because these sigmas kind of represent how much information we captured. And so once we have maybe 99%, we can cut off there, and that will determine our R. But actually what we're going to do in this session is look at how we can have a mathematically proven optimal way of doing this truncation under certain conditions. So that's what we're going to get to later in this session, but for now, let's have a quick recap of what eigenvectors and eigenvalues are. And we're going to use these to compute the SVD by hand. So, eigenvectors and eigenvalues. Let's start with the definition. So, if we have a, it's going to be a square matrix A. So, eigenvalues and eigenvectors only exist for square matrices. Square matrix A. Then an eigenvector. So an eigenvector is a vector V. I'm going to leave a gap there, such that when we times V by A, so when we kind of transform V through the matrix A, we end up with a multiple of the original vector for some value lambda, which is just a real number. And looking at this, we can see, well, actually, this would hold true for V being the zero vector. If we take, the zero vector and map it through anything, we still get the zero vector. So we're going to make the condition that V is not the zero vector. Otherwise, it's quite boring. So that's what an eigenvector is. Let's think about what that means geometrically. So let's say I have some sort of, so let's start with our vector space here. Let's say we're in 2 dimensions. And let's just draw kind of these coordinate lines here. There was something like this. And we have a cross here as well. So this is just kind of a lattice grid of what our coordinate space looks like. And then we're going to transform this using the matrix A. So A is a linear map. It kind of transforms the space. And we're going to transform that into a space where the verticals are still vertical, but all of the x's, kind of the horizontal lines, have been skewed slightly. So now they tilt upwards a bit, like this here. Okay, so we've basically taken this kind of flat space like this and just tilted it up slightly. That's what our matrix A is doing. So you can imagine we have a vector V1 here. Well, that's going to get mapped to, okay, let's make sure this green one here goes through the middle. Doesn't seem to like that. There we go. Okay. So where's that going to get mapped to when we map it through A? That's going to end up at this point here. We can see that by just mapping the grid lines. You know, this was 2 across, 1 up, 2 across, 1 up, but now our across is slightly skewed. So this is now the vector AV1. And we can see here that this is not a multiple of the original. Like when it's a multiple, it points in the same direction. It could be longer, it could be shorter, but it points in the same direction. That's not the case here. But if we take a vector here, v2, and then we map it across to here, this is AV2, we can see these point in the same direction. And so for that reason, this vector v2 is an eigenvector. In other words, it's yes, it stays in the same direction after being mapped through the matrix A. And the amount it gets scaled by, here it was scaled by a factor of 1. It didn't change its size at all. The amount it gets scaled by is known as the eigenvalue, and that is this lambda here. Okay, so hopefully that's something you've seen before. Let's just have a quick reminder of how we compute an eigenvector and eigenvalue pair. So we have here that an eigenvector satisfies this equation for some lambda. Actually, let's do this in the correct color for this. Black. Okay, so we have, let's get this correct as well. AV is lambda v. So that's the definition of an eigenvector, has to satisfy that. And so let's take that and let's write it in this form. So AV minus lambda v is the 0 vector. And now let's just throw an identity matrix into the middle here. So the identity is basically the 1. In the same way we can times by a 1 at any point in maths, we can times by the identity at any point in linear algebra. Still is 0, and now let's factorize this. So a minus lambda I times v is 0. So we just took the v outside of a bracket there. You can see it still expands to the same thing. Okay, so we have that this matrix here times by v is 0. Okay, well we have that the definition of an eigenvector is that it's non-zero. So let's suppose that a minus lambda I was invertible, that it had an inverse. Well, then we could invert it, take it over to the other side. We'd have 0 times a matrix, and so v was 0. So we failed there because v is not 0. So it must be the case that this is not invertible, because if it was, then we run into trouble there. And another way of saying it's not invertible is that it has a determinant that is 0. So in other words, the determinant of a minus lambda I is 0. And then this gives us something called the characteristic equation. So the characteristic equation of A. And then we want to solve that for where it's 0, and then that will give us the lambdas. And then we can kind of back solve it to get what these vectors, these eigenvectors v, are going to be. So hopefully that's something we've seen before at A level or at university maths. Now we're going to introduce a slightly different idea. And what we're going to do, let's say we have eigenvectors v1 up to vn, and we have the corresponding eigenvalues lambda 1 up to lambda n. What we're going to do, we're going to make a matrix V which has these eigenvectors as its columns, and we're going to write A times V. Okay, and we know that what that's going to be is a matrix looking like this. So it's going to be A lots of V1, A lots of V2, all the way up to A lots of Vn. So we just apply that A to each of those vectors there. But we know, because these are eigenvectors, that this is the same as lambda 1 V1, lambda 2 V2, all the way up to lambda n Vn. Okay, that's just the definition of an eigenvector. And then from there, we can observe that this can actually be written in this form. So V1, V2 to Vn, these column vectors we started with, times by this matrix here, all the way down to lambda n. And so have a look at this and convince yourself that this is true. This here is our matrix V, and this here we're going to define to be called capital lambda. And so we then have that this is equal to v and lambda. So if we ever see something like this again in the session, and we will, that's a hint, if we have AV equals V times some diagonal matrix, so this is diagonal here, then that tells us that V is a matrix of eigenvectors of A, and this capital lambda is the eigenvalues that correspond to those eigenvectors. So that's going to be very useful. Okay, but let's move on to now, for now, to understand how we can compute the SVD. So computing the SVD. Okay. So I'm going to offer a method of computing the SVD that is based around using the correlations between the rows and columns in the original matrix X. So this is a very inefficient way of calculating it, but it's quite simple conceptually. And so we'll do this, but bear in mind, in practice, you would never use this method. It's inefficient, and if you're doing it by hand, it can get quite messy. So what we're going to do, we're going to look at the matrix X transpose X, okay? And we call this the columnwise correlation matrix of X. And we'll see there's also a row-wise version. So remembering what X looks like, so X was this matrix X1 up to XP of these observations. And so X transpose is going to be this matrix here of rows going across like that. Okay, and if we remember from our definition of matrix multiplication above, like this is going to give us a matrix of inner products. It's going to look something like this. So X1 transpose X1, all the way up to X1 transpose XP, XP transpose X1, and all the way going to XP transpose XP. That doesn't look right. Okay, these should have all been n's. Yeah, and each of these has a length of p, but we only have n observations. So sorry for any confusion there. Okay, those are both n's. Okay, so this is kind of a way of representing all the kind of information between the similarities between our vectors x. So if we remember, so these are inner products here. We defined them in the first session. And these kind of correspond to the kind of the similarity between two vectors. So when these numbers are very big, it means that the two vectors kind of point in similar directions and so are quite similar. And when it's 0, that's the smallest it can be. No, sorry, that's not true. When it's negative, that means they point in really different directions. And so this is kind of a matrix capturing all of the similarities between the different observations at different times. So, for example, back to the faces example, where each of these x's represents someone's face, if xi transpose xj was big, that means there's a lot of similarity between the ith person and the jth person's face. So this kind of captures all those interactions in one single matrix. And what's nice is that this matrix here is n by n, whereas x itself was a p by n matrix. And so all that kind of information is captured in a smaller matrix, which is really nice. Okay, so some even better things about this matrix. So it can be shown that, well, one, this matrix is symmetric. That's good. And it's symmetric because when we take these inner products, we could just reverse the order of each term in the product inside the sums. So they're all, you can reflect these across the center line. It's symmetric. And it's also this thing called positive semi-definite. We're not going to get into what that means. The proof of that is very easy. Basically, we just write v transpose x transpose x v as x times v transpose x times v, and define this to be y transpose y, which is non-negative. So that's, if you know what positive semi-definite means, that's the proof of that. Very straightforward. Don't worry what that means. This is a time you can just trust me that what these two properties imply is that it has, so yeah, it is diagonalizable, and the eigenvalues are non-negative. Okay, so that's good. That's, you know, those are helpful properties, and we'll see in a second. So what we're going to do now, we're going to look at x transpose x, but using our singular value decomposition. And specifically, we're going to use the economy SVD. So we're going to have that x transpose x is u hat sigma hat v transpose. We don't need to make v economy, it's already the right shape. And all that transposed, and then u hat sigma hat v transpose. Okay, well, we can take out that transpose, so now we have v sigma hat u hat transpose and u hat. We have sigma hat again. Well, sigma hat is symmetric, so the transpose is the same thing. And finally, the transpose at the end. But if we remember, even though this u hat is not orthogonal anymore, it is semi-orthogonal in this direction, so transpose coming first. And so actually, this u hat here is the identity. And so we're left with v sigma hat squared v transpose. Now v is orthogonal, so we can times by the inverse, and that's going to get us x transpose x times v is v sigma hat squared. And so hopefully this will be a bit of an epiphany moment, because you'll remember what we saw here. AV, V, and then a diagonal matrix. V gives us the eigenvectors, and its diagonal gives us the eigenvalues of the matrix A. And that's exactly what we have here. So this V matrix here, this is the eigenvectors of x transpose x. And then here is the eigenvalues. And just a reminder of what sigma squared looks like. Let's put this somewhere else. So sigma squared is going to look like this. So taking each of the singular values and squaring those. That's what happens when we square a diagonal matrix. Okay, so that's looking really good, because now we could calculate the eigenvectors and eigenvalues of x transpose x. You know, this is not a massive matrix, it's n by n, rather than having any p's in it, where p is normally massive. So we could calculate those eigenvectors and eigenvalues, and then that gives us v and sigma. Now we could do a similar thing by looking at x transpose, and if you work through the maths, that's going to give us, well, actually, if we do the same thing for that, we'll see that x transpose of u is hats here is sigma squared like that. So that's nice. But the problem with this is that this x transpose is a massive matrix. This is a p by p matrix. And so although we could get the values of u using this method, we would not want to, because this matrix probably can't even fit in memory, or if we're doing it by hand, it's going to be a nightmare. Okay, so instead what we can use that. So x is u hat sigma hat v transpose, and so that implies that u hat is x v sigma hat inverse. So once we have v and sigma, which we can get from this n by n matrix x transpose x, then from that we can get our u. So we have the single value decomposition, great stuff. So we're now going to get on to actually computing this SVD, an example of it. I apologise again, we're going to run over a bit, maybe about 15 minutes again. We're going to have a break now for just a minute or two, just to give you some time to let that sink in. Then we'll come back with an example, and then what else are we going to talk about? An example of that, and then we'll talk about some other methods of computing the SVD, and then how we can find the optimal R to cut things off. So we'll join back again in a few minutes. Okay, so let's apply this to an actual example now, see how we would compute the SVD by hand. So we have this example here. It looks very contrived, and I deliberately set it up to give us nice answers. Generally, the SVD doesn't give us the prettiest of answers, but this will do for now. And we'll see next session how to compute it using Python and other languages. So the first thing we're going to have to do is compute X transpose X. So this will be a 3x3 matrix. I'd much rather work with that than the 4x4 matrix that is X transpose. And that's going to be the inner product of all of these columns here. So we're going to have the inner product of the first one is going to be 9. Or you could compute this just by doing the matrix multiplication, but I'm going to kind of use my kind of head for this. The inner product between 1 and 2 and 1 and 3 are 0. This is going to give us 1, 1 and half, so 5 on 2. And then 3 on 2 because we negate it. No, that's going to be 5 on 2 as well. And then it's going to be 3 on 2 for the other. So I'm rushing through this just because I don't want to waste your time working on algebra. But you could compute that for yourself if you wanted to verify that. So looking at that matrix, we can instantly spot that that 9 is an eigenvalue. And the reason for that is because we have this kind of, it's almost like a block matrix with a 1 by 1 at the top, 2 by 2 at the bottom, separated by all zeros. And so from that, we can get that lambda 1 is 9. So my screen is frozen now, and we'll come back in a second. I'm just going to talk through the rest of it. So now what we're going to do, we're going to take this this matrix at the bottom here, so 5 over 2, and we're going to subtract away the lambda identity. And we're going to leave the non-diagonals as they were before, and we're setting this equal to 0. Okay? And so this is going to give us 5 over 2 minus lambda squared, if you remember how to do your determinants, and 9 over 4. So that should be just subtracted away. Okay, so multiplying this out, we get 25 over 4 minus 5 lambda plus lambda squared minus 9 over 4, which is going to give us 16 over 4, which is 4, minus 5 lambda plus lambda squared. And so factorizing this, we're going to get lambda minus 1 and lambda minus 4. And so our eigenvalues are 4 and 1. Okay, great. So now we have to find the corresponding eigenvectors for those. So again, just by inspection, I can see that the eigenvector for lambda 1 is just going to be 1, 0, 0. And then for lambda 2, which is 4, we're going to look at the matrix, which is going to be 5, 0, 0. So we're going to take 4 off all of the diagonals. Hopefully you're fairly familiar with this sort of process. 5 over 2, 3 over 2, 3 over 2. And then that implies that the eigenvector for V2 is going to be, what's that going to be? Well, we're going to have to add that and add that. Oh, wait, sorry. Forgot to take off this here. minus 3 over 2. That implies they have opposite signs. So it's something like 1 and 1. And then I can tell also that because these are going to have to form an orthogonal matrix, that V3 must be 0, 1, and minus 1. So again, I'm using some kind of inspection to do this. You could do this the formal way if you had more time. And so the problem that we have with this is that the matrix V is an orthogonal matrix. And so we need to make these have length of 1. So we're going to just normalize these to be 0, root 2 over 2, root 2 over 2. And this one's going to give us a normalized version of 0, root 2 over 2, and minus root 2 over 2. Okay, so that has given us our vector V. And these are going to be the rows of V. So we're going to end up with the first one, 1, 0, 0, then 0, root 2 over 2, root 2 over 2, 0, root 2 over 2, and then minus root 2 over 2. Okay, so that's our V. And our sigma is the square roots of the eigenvalues, because sigma squared is the eigenvalues. So we have 9, 4, and 1. So we have 3, 2, and 1, like that. And so now I'm going to leave it as kind of an exercise for you to compute what U is. So U is going to be, oh sorry, this is the hat version, the economy SVD. U hat is going to be X, that's V transpose, XV sigma hat. You can compute that for yourself. And what did I get? I get for that. So if you do the work for that, we won't do it now, you'll end up with this matrix here. So 0, 1, 0, 0, root 2 over 2, 0, root 2 over 2, 0, and 0, 0, 1. And if you want, you can then, wait, sorry, was that? Yeah, that's fine. And if you times those all together, you will get back to X to kind of verify that it was correct. So that's how you would compute that. A few kind of skipping steps there, but that gives you the general idea of how you can go about doing that. Okay, so problems with that. That is really inefficient. You do not want to be doing this in practice, even on a computer. For very big matrices, that will take absolutely forever. And so a better solution is using another decomposition as kind of the introduction for this, or the foundation. And so you can use this thing called the QR factorization of the matrix X. And that's going to give us a kind of a starting point that will make it a bit easier to work from. And so you might have come across the QR factorization. One method you can use to compute it is using the Gram-Schmidt orthogonalization. But be wary of that. It's a very numerically unstable method. And as the number of observations or predictors gets big, your numerical error, your approximation error, is going to grow pretty massively. There's another method using reflections, but it's a bit more complicated. Do just bear that in mind. Now, there's still a problem with this method. And that is, what if X is massive, like really, really big? Because the problem with the QR factorization is that we need to be able to hold the whole of X inside of memory. And if P is really, really big, we're not going to be able to do that. So in this case, this is maybe the one exception, it's okay to do the this method of using correlation matrices. And we do it using a method called the method of snapshots. So let's go back to here. So X is massive, and the idea is we can never load X in memory, the whole thing at the same time. But what we can do is we can pick out one row and one column of X at a time. Multiply those together and use that to fill in all the elements of this correlation matrix. And remember, the correlation matrix is n by n. So P is the really massive number that's causing problems. So this matrix, we can store this in memory, no problem. So we've got around the massive P issue there. We then can calculate the eigenvalues, eigenvectors, no problem. It's an n by n matrix. And then when we go to calculate what U is, using this inverse method, we simply calculate X times V, and then that times sigma inverse, one piece at a time. So again, a very memory constrained way of doing it. So this is known as the method of snapshots, and it's the one case where actually this is a good way of approaching it. When your data, when your P is so big that you just can't store it in memory. So there's also one other method that we're not going to talk about in this session, or this whole series, called the randomized SVD. This is an absolutely genius method, very recent, and it's a way of computing the SVD. And it's a stochastic random method that might not get you the right thing, but will get you close, but it's way more efficient. And it works by taking random projections of your matrix until it stabilizes. I guess you can think of this as like stochastic gradient descent, or stochastic least squares for regression. It's that kind of idea of using randomness to get a more efficient solution. So have a look into that if you're interested. It is a beautiful algorithm, and randomized linear algebra in general, it's a very new topic, kind of really hot this decade. If you're looking at doing a PhD, might be something to look at. So please do have a look at that. And so the final thing we're going to look at is this thing called optimal truncation. Optimal truncation. Spell that correctly? Okay. And so this comes down to what R should we pick to truncate our singular value decomposition. So we saw here two methods, one using this Elber method, one using this percentile. And they're good, but there's no real theoretical backing for them. And it would be nice to have a method that we could prove to be true under certain conditions. And so we have just that. And it is a method by Gavish and Donahoe. And this was published in 2014 in the IEEE journal. Okay, and it's worth having a look at this yourself. It's very approachable. All the code is included, so definitely have a look at it. And it works under the assumption that your matrix X can be decomposed into two parts. There's an underlying true signal. This is the actual thing you want to represent, plus some noise. And this noise matrix, the exact properties of this, is that each element of this noise matrix is independent, identical, normal noise. Basically, this is just a noise matrix, random white noise. And then also there's this value gamma, which says how much noise is there, kind of as a ratio to how much true signal there is. So if gamma's big, it's mainly noise. If gamma's small, then we mainly have the signal we care about there. So that's the assumption we work under. And it turns out to be a very good assumption for any large data. That basically most large data satisfies this assumption here. And so then what we can do is we can do this this log sigma I plot with a certain rank. And we can do this for simulated noise data. So what we do, we just take some noise, and we compute noise a lot of times, and we plot what the singular values of the decomposition looks like for that noise. And it tends to look something like this. Let me get this right. So a small lip, and it flattens out to 0. So that's kind of what we would expect if our matrix was entirely noise. And then what Gavish and Donahoe did is they plotted some kind of real data and found that the graph of sigma I, or log sigma I, looks something like this. So basically, for the low end, it looks an awful lot like noise, and then as we get to the high end, it starts to split up. And then the idea is that we take this thing called the noise floor, and we define this by, it's the maximum single value of the noise matrix. That is our noise floor. And then we make the assumption that everything above that noise floor, that is our actual signal. And then anything below that, well, that must be noise. Okay, so that's the assumption we work under. And it can be shown that actually, if our data does have this this form here, which is a reasonable assumption to make, this Oh, sorry. So then what we do with this is that we then take where this noise floor crosses our singular values, and that is the place we truncate. So it's kind of any singular value that is bigger than the noise floor, we keep it, otherwise we remove it. And it can be shown that actually this is optimal. If our data has that form, which is again a reasonable assumption, this is the optimal truncation you can do in terms of the Frobenius norm. Okay, so then in this paper, Gavish and Donahoe go on to prove multiple cases. We're going to look at the simplest and the most complicated. So the simple case is what if X is a square matrix and gamma is known, so gamma being the amount of noise. This is a very rare case to have in real life. It's rarely the case you have square data, and why you would know kind of the ratio of noise to data is very unlikely, but you might. And so then what we do, we define our noise floor, so this kind of dashed line here, to be the symbol tau. And tau is given by a very simple formula, which is 4 over the square root of 3 times gamma times the square root of n, where n is the size of our matrix. So an incredibly simple property, quite beautiful even. I mean, the derivation is a bit tougher, quite involved, but that's it. That if you know your matrix is square, you know there's gamma, that is the optimal place to truncate. And so from that, you have this best representation, best low-level representation of your data, which is great. So let's look at the more general case. Actually, this is the most general case. And this is when X is general, so X is square, rectangular, whatever, and gamma is unknown, which is much more likely. In this case, the expression isn't as simple. Here we have a noise floor. Well, actually, no, let's first define something else. So what we're going to do, we're going to take our, let's plot this one again. We're going to take our singular values that we see. It's worth mentioning this red line, we can't see that in practice. This is simulated over loads of bits of data, but we can't see that when we actually plot the singular values. We only get this green line here. And then what we do, we take the median singular value. So we're going to call this sigma med for median. As we take that, this lies 50% of the way through our rank. And so we call this sigma median, and then we work under an assumption. We're going to define a parameter beta, which is going to be the aspect ratio of our data. So it's either going to be n over p. Sorry, it's going to be the maximum of n over p and p over n. So basically, kind of what is the aspect ratio of our data? We make sure it's bigger than 1. It's the aspect rate ratio. And then what we do, we then, using some theory, we fit the best noise curve based on what the median value is and what the aspect ratio is. So we'll fit some noise curve, something like this, under the assumption that that sigma median is in the noise. And that's a very reasonable assumption to make, because we assume that at least more than half of our data, or kind of the last half of data, we can represent it with at least 50% efficiency. And so we fit the best noise curve using that, and then we use that as our noise floor. And then this gives us kind of an empirical value of the noise floor to be, it's a very simple equation involving a very complicated expression. So it's this omega of beta times by whatever this median value is. And all this is here is a correction factor for the aspect ratio. Now, the actual expression for this is really complicated, and I'm not going to get into it. But basically, it's as simple as, take this correction. Once you know that, it's simply just a factor of whatever your median value is. And again, this is proved to be optimal under the assumption that you don't know your gamma, X is any shape, and it satisfies this above highlighted thing. So that is absolutely gorgeous. And actually, that's where we're going to leave things off today. that we now know how to calculate the SVD, we know where to truncate it, and now all we're left to do is actually to apply that to some problems. So we'll join again on Friday for the final session where we're going to get a bit of Python coding, and then we'll get other examples sorted for later. It's worth mentioning at this point, if you are a competent coder in MATLAB, Julia or R, and would want to help out with actually translating, or I guess any other mathematical language, you want to help out with translating the Python code into other languages, get into contact with the society. We would be very happy to take on your support. So with that, thank you for coming to today's session, and I'll see you again on Friday.